This video presents our paper, Learning to Double Guess. We start with the assumption that our robot has firmly grasped onto an object and we can pick it up to get an initial first-stroke reading. We can then pass through the first-stroke reading through a Bayesian Neural Network to get a three-dimensional XYZ center of mass estimation and its standard deviation. We will use those information to perform a grid search through a active net to estimating the next best orientation to rotate to improve the center of mass estimation. Then we will pass through that second reading through the same Bayesian neural network to get two center of mass estimation and their standard deviation. We will assume those two are the different measurements of the same physical property and perform a joint distribution with them to get the final prediction of center of mass. As seen from the picture, the final prediction is much closer to the ground truth than any other previous estimations. We only collect data on two of the customized 3D printed objects, a box and a plate. We only collect a total of 204 graphs with different location of center of mass and a total of 18,000 different first-stroke readings from different orientations. Here we show an example of data collection process where we rotate the box shape to 100 different rotation orientation and collect first-stroke sensor reading for each orientations. We also need to rotate empty-handed to those same 100 orientations because we only want the first-stroke reading changes caused by the object itself. In online test, we first collect the empty-handed first-stroke reading before graph, then we graph on the object, get the first-stroke reading, and estimate the best action. After we rotate the best orientation next and get the second first-stroke readings, we will need to rotate empty-handed again in order to get the difference between the two first-stroke readings in order to run our algorithm. We perform 5 different graphs on each object, and we tested on 12 different objects in total. None of the objects has been previously seen by our algorithm since we only collect data on the customized objects. And all of the objects we tested is very common in our daily lives and it's very easy to find. Our algorithm shows an improvement overall of our Bayesian method and can achieve less than 7.6 millimeter error from the ground truth center of mass location. The error percentage is as low as 6.9% if comparing with the largest dimension of the object. Overall, we show that our algorithm can robustly estimate center of mass and step towards robust robot manipulation.